So this is our second of only 2 lectures in this chapter, which is an introduction to convection. It's all about boundary layers, and we talked about the velocity or momentum boundary layer and the temperature or thermal boundary layer, and talked about the boundary layer thickness and growth. I tried to talk a little bit about average and local coefficients, and I purposed not to talk about laminar turbulent. Today I talk about it. So we do have the boundary layer equations. This can be very mathematical in this section. The dimensionless groups, we'll emphasize them. I've been trying to emphasize them, but you want to come up to speed on that. But there's so many of them that it's good to have a table available to refer to dimensionless groups. We're going to end on an analogy between heat transfer and momentum transfer. It's called the Reynolds analogy. It has been modified by Colburn and Chilton, and some other people contributed to the modification to help it fit experimental data. It's limited in its application, but it's very powerful. Let's jump into it. So I thought I'd just start a problem that emphasizes difference between a local value and an average value. So if you're given the local convection coefficient H, just magically it's given this way, and you can see it's a quadratic equation. And H is a function of x. And if I plotted H as a function of x, it would go from 0 out to some distance. You could see that I'm going to stop it at 3 meters. So 1, 2, 3 meters there. So we're really interested in H as a function of x over the range from 0 to 3. You can probably evaluate this at 0 pretty quickly. What's the value of H at 0? 25. And with a little bit of work, you can evaluate the H at an x of 3. You just stick into the equation, and it would come in right at 7.6. So it'd be down here, 7.6. So it goes from 25 to 7.6. It's not linear. It's like quadratic. Okay, concave down because of the negative 0.6 x squared. So the first part is real easy. Just stick in the value. But what about the average from 0 to 3? Well, look at your numbers. It shouldn't be over 25, and it shouldn't be less than 7.6. So when you do the math, you can always check. So the equation to calculate the average H between 0 and 3 would be the integral from 0 to 3 of h of x dx. And then you divide by 3 minus 0, or 3, 1 over L. The length is 3. And when you calculate that average from 0 to 3, you get it's 17.2. Now, what about the average from 0 to 1? What do you think? Less than 25? How about greater than 17.2? Yeah, it should be. So you go h bar 0 to 1 is equal to 1 over 1 minus 0, the integral 0 to 1 of h dx, and it's a mathematical exercise. It comes in at 22.8. How about the average between 2 and 3? It's still only 1 meter average, but instead of going 0 to 1, you go from 2 to 3. So that computes to be about 11.2. This is almost too trivial for us, right? But the difference between a local value and an average value. That goes for shear stress at the wall, goes for convection coefficient, goes for a Nusselt number, goes for the skin friction coefficient. So end up, you get a lot of equations. If you didn't know, I'm not too keen on doing math by hand when you can have a computer available. So that's just implemented in alpha, Wolfram alpha. So let's continue on. So now we want to talk about or review from your fluid mechanics difference between a laminar regime and a turbulent regime. These are flow regimes, aren't they? Meaning the behavior in that type of flow regime, that's a grouping of flows, looks similar, or they have similar characteristics. That's what we mean by a flow regime. So think about the fluid packet. The fluid packet in the laminar flow stays in the layer. What does it do in a turbulent flow? Breaks out of the layer that it's originally in. So if we have a plate right here, and we have fluid flow flowing for it, maybe I should have even shown the plate way over here. Let me get this color right. Here's our plate, and the fluid is approaching it. So if I have red dye and I taint this one, there's nothing to make it jump outside of its layer. It's laminar flow approaching it. And then it stays in that layer even though the boundary layer may grow like that. Okay. That's laminar flow. It comes from the word like lamina. Lamina going back to like geology and sediments and laying down of rock and soil in different layers, and it's the same for fluid mechanics. What keeps the fluid in that packet, and what would make it want to break out of that layer and go to a different layer and bounce around? Yeah, the viscosity is what holds it together. So the viscosity in laminar flow is high, or the viscous forces or viscous stresses are high. But the inertial characteristics, or the inertial forces or inertial stress or inertial pressure, is low. Well, just opposite when they get over here. So the viscous forces or stress are lower than the inertial stress or pressure. That's high. So what happens is a little fluid packet can break outside of its layer, and there you go. We have turbulent flow. What we find is flow over a plate, maybe gets to a location, roughly in this location, the flow transitions from being laminar to turbulent. Almost, well, all flow starting, and if it's coming and approaching the sharp knife edge plate without already some turbulence, if it's flow, it's, in wind tunnels they work really hard to get rid of the turbulence as it approaches some test section. So they'll put flow straighteners in the wind tunnel. So you're not coming in with a bunch of turbulence, but when you hit that plate, it'll stay laminar. And then what will happen is you'll get to a transition, you'll get turbulent flow. So what's a characteristic? It acts like it's chaotic. It acts like the packages are going here and there. So any instant in time, if I focus on this location, the fluid velocity could be this way or that way or this way or that way. Now the time average velocity at that location will be in the positive x direction, but the instantaneous velocity could be all over. That encourages mixing, encourages transport of properties more rapidly through that layer. Well, what's interesting is once you get it out into that core region of the turbulent boundary layer, it's easy, but you still have a laminar sublayer. And then that laminar sublayer, there's a lot of restriction or a lot of resistance to the transport of the momentum. So we could plot something like the shear stress at the wall, tau sub s, and a function of x. It's going to go down, but then it kicks back up and then goes back down again as that behavior. Initially there's a boost and it's higher in the turbulent region. If you wanted a large drag force or a large convection coefficient, you'd want to make it turbulent. The laminar part is like a layer of insulation or layer of prohibiting the flow. So that's a review of fluid mechanics. We characterize this by a Reynolds number, do we not? So what is the Reynolds number? The ratio of competing forces. What's in the numerator of that ratio? Inertial. And in the denominator? Viscous. So the Reynolds number is inertial. Now, what would be the inertial? That would be something like 1/2 rho u infinity squared, but you could just forget the half because we're just scaling here. So it's proportional to rho, the density, and then u infinity squared. If I bring fluid to rest, I will have a higher pressure. That increase in pressure is the dynamic pressure 1/2 rho u infinity squared. So that's our inertial force per unit area. So we put that in the numerator. We'll have rho u infinity squared. What about the viscous? Well, we think of the viscous shear stress is mu, the change in u per change in y. Well, approximate that derivative. So the viscosity, you would think, so u infinity minus u naught or 0 at the surface, no slip boundary condition. And then we got to divide by some thickness. Well, this is where it becomes more difficult, and that's why the Reynolds number doesn't break at 1 or something like that. It's hard to get a good length scale for true scaling. So what you do is you grab any length scale that's of value or interest or that's readily available. X, if you're doing flow over a flat plate, that's the distance from the leading edge. Or D for diameter, or some other length scale. But if we put that in here, we'll get mu, u infinity, x. We cancel one of the u infinities, and there's our traditional Reynolds number. Its length scale is x, so it's rho u infinity x over mu. A little abstract, isn't it? What's it a ratio of? Inertial to viscous. Well, we're going to write the boundary layer equations in the laminar part of the boundary layer. And these are the boundary layer equations. Two of them you're very familiar with, aren't you, coming out of fluid mechanics? And so what is this first one? What is its name? Oh, very good. It's continuity equation. This equation right here is the two-dimensional continuity equation. It is a statement of the conservation of your choices are velocity, linear momentum, mass, kinetic energy, or total energy. Is everybody in? You're all good? All right. So let's recall. It's a statement of the conservation of mass. That's exactly what the continuity equation is. Well, I can't go back and redo everything in fluids. So please, if you're a little spotty there, pick up the book, spend a little time looking at it, right? So this equation comes from something like the change in density with respect to time plus del dot rho u equal to 0. What is this del dot? I forgot mathematically. What's that called? Okay, clicker question. This is either the div, grad, curl. Answer A, B, or C. Del dot is either div for divergence, grad for gradient, or curl for curl. Which one is it? Is everybody in? All right. So somebody says, why didn't you say del? Okay, answer D, del, but it's wrong. Del is just this symbol. And then you put del dot. Ah, now we're talking. What is that dot right there? Well, that's a dot product. You treat this del as the partial with respect to xi plus the partial with respect to yj plus the partial with respect to zk, and you dot that with the velocity vector. That's the ui plus vj plus wk, and then you pick up from this term the partial of u with respect to x plus, now I forgot to put the rho in there, so let's put the rho and the rho and the rho. So you put the, okay, fine. Pull that rho out because it's constant and cancel that because it's constant. Great. So if I do del dot u, right, then I pick up the partial of u with respect to x plus the partial of v with respect to y plus the partial of w with respect to z, and that's equal to 0. This is 2D, so forget the third dimension, and that's our continuity equation. And so this is the divergence. It measures the spreading of that vector field, or the concentrating of that vector field. Right? All right. So once we get our continuity equation, conservation of mass, and we get this second equation. What is this equation a representation of? Linear momentum in either the x or the y. It's either in the x or the y. X. It's in the x. Because if you think about it, there's a lot of action happening in the x. The fluid's coming in and then dramatically slows down as it's flowing over the surface. And because of the gradient, u is changing as a function of y, we have viscous transfer of momentum. So this is linear momentum in the x direction. And then this would be really the new equation. This is it. I mean, it's just the energy equation. But can you see the parallel here? What is this term for the linear momentum and what's this term for the energy? Can you see that? How do I describe both of those? Diffusion or advection? They're advection. They're the sweeping through, the moving through. Sometimes there's a particular derivative in fluid mechanics that has a big letter D. You know, it's like d dt. What is that derivative in fluid mechanics? Material. It has about 6 names. Material derivative. Another name. Total derivative. Any others? Substantial derivative, material derivative, advective derivative. I mean, there's just a pile of them. Even probably I've seen convective derivative. And I'm probably missing a few. But anyway, that is how it's sweeping through the system. Take a look at this term and that term. Can you see the comparison, the analogy? What does this represent? What's the nu? What is the name of the property nu sitting in front? Viscosity. It's kinematic viscosity. And so it's diffusion of linear momentum through the viscosity. The faster fluid on top of the slower fluid is going to want to speed up the slower fluid. And conversely, the slower fluid is going to want to slow down the faster fluid above it. Okay. So there's a transfer of something. Linear momentum. What do you think this is? Transfer due to diffusion of energy. Because what's alpha? It's K over rho. See, it's a normalized thermal conductivity. It's diffusion of heat. All right. Now, what about this thing? That's why I try to avoid saying it's the statement of the conservation of linear momentum. I'll say it. A lot of people will say it. But F equals ma, or F equals the time derivative of mv. If I say this equation, you say, oh, Newton's law, second law, right, of motion, right? That's all this is right here, this linear momentum equation. Isn't mv the linear momentum? Yeah. If you want to make it a vector quantity, that's great. Make it all a vector equation. mv, sometimes I wrote it as p. That threw me for a loop in physics. It's like, oh, great. P, another symbol. It's not pressure. P is mv. It's a linear momentum. But this is how it changes as a function of time. How can it change for a particle? You can apply a force to it. Have a force imbalance. Will the linear momentum change? You bet. It'll go up or down depending on the imbalance of force. Same thing over here. This is the equivalent of some force as well as that, some force to accelerate or decelerate the flow. This is coming from pressure gradients. Pressure gradients. Now they didn't write down the y equation for linear momentum because it boils down to that the pressure external to the boundary layer penetrates the boundary layer, and the pressure, which in general could be a function of x and y, is, for the boundary layer over a sharp edge plate, a function of x only. Hence, the partial derivative pressure with respect to x boils down to ordinary derivative of the pressure far away with respect to x. So there's a lot of discussion in here which I'm glossing over. It's fluid mechanics, and I know that's in the fluids book as well. But all we added was the energy equation. One last term that I didn't talk about is this term. This is the tough term. This term right here, what is that term doing in this energy equation? It is often equal to, what would you like it often to be equal to? Zero. And it is. But everybody will ask this question. Okay, you're doing an energy balance, but it's only a subset of the energy. It's not a kinetic energy balance. This is an heat balance or internal energy balance. I know it has specific heat constant pressure, so like an enthalpy balance. But if you have a lot of kinetic energy, you can dissipate that some, and it shows up into the heat transfer equation into the energy balance. Here it is, it's showing up. This is viscous dissipation. Sure doesn't look like it, but that's viscous dissipation of mechanical energy, and it shows up into our energy balance equation. They show it to you, but very often it's equal to zero. Did I say very often? It's extremely rare in this class it would ever be anything but zero. I can't remember a problem or a time when it wasn't zero. But it's nice to be shown where it shows up and why it's there. And then say, bye-bye. Okay. We already answered that. So what we do is there's a lot of math to cast these into dimensionless form. What are the big equations? The velocity or linear momentum equation, the thermal or energy balance equation. We threw out the viscous dissipation term, and you then cast the boundary conditions in dimensionless form at the wall and the free stream, and you observe the similarity variables that really drive the flow. That's why the Reynolds number characterizes, that shows a lot about the shear stress at the wall, and it shows a lot when it's laminar, turbulent. It shows up right there in our equation in dimensionless form. When you do it for the energy, it shows up a parameter which is a Reynolds times a Prandtl. Same Reynolds number times the Prandtl number nu over alpha. If you can solve for the dimensionless conservation equations, you can then express the skin friction coefficient, what we're really interested in to help us predict drag force, as 2 over the Reynolds number times, and then this is the derivative of the dimensionless velocity at the wall. At the wall. So solve for u star, the dimensionless velocity, and then take the derivative at the wall, and now you have the local shear stress and the local skin friction coefficient. Same with the Nusselt number. Here's a general definition of the Nusselt number, but if I had that temperature, that dimensionless temperature ratio difference, divided by, or take the derivative with respect to the distance y out into the through the boundary layer, that would give me the local Nusselt number. I pause. That was a lot. But do you see the scheme? Governing equations, solve for them, get the temperature distribution, the velocity distribution, differentiate it, evaluate it at the wall, and they get what really is of interest, the local skin friction coefficient and the local Nusselt number. The local tau, the local H. So, as a review, make sure that we can do this. Our Reynolds number, you can talk about up to X, or the Reynolds number at L. Let's say L often is the trailing edge. The friction coefficient, local. The friction coefficient average, especially over the plate, 0 to L. The Prandtl number is just the Prandtl number, and that Nusselt number, you can have it as a function of X. What was it? Hx divided by K. Sometimes they'll put an F on that because it's the fluid thermal conductivity, or the Nusselt number averaged 0 to L, H average L over K sub F. So the game, it seems a little funny, but we're going to try to find relationships for the average Nusselt number, the average friction coefficient, as a function of the parameters that drive those differential equations. So what drives it? The Reynolds number. And so what we look for is you just turn this equation around. C sub F times the Reynolds number divided by 2 is a function of the Reynolds number. Likewise, this equation, the Nusselt number, is equal to a function of the Reynolds number times the Prandtl number. It's really multiplied. The Prandtl number and the Reynolds number together, they're multiplied there. Okay. Now, if, this is a little bit of the magic getting to the analogy, if the Prandtl number is around 1, then I could rewrite this as being a Prandtl number, not just the Reynolds. I could rewrite it in the velocity or linear momentum equation is Reynolds times Prandtl. So right here I could put times PR, and I could put times PR right there. It's a little bit of magic. And then if I say that the pressure gradient is negligible, and then I look at this equation and that equation, they're the same equation. And the boundary conditions were the same normalized boundary conditions. Hence, the solution, F, is the same. I just went 90 miles an hour and flew a jet airplane, Mach 10 over your head. Pew. But this is the key thing about the analogy between the heat transmission and the linear momentum transfer. So what we do is we say, ha, look at that. You mean I can write C sub F divided by 2 times the Reynolds Prandtl is equal to the Nusselt? You sure can. And a lot of people won't write it that way. They'll bring that Reynolds Prandtl over here to that side. And you're tired of new names, but they'll call this the Stanton number to honor somebody who did a lot of work in the field. So we honor Prandtl, we honor Nusselt, we honor Reynolds, we honor Stanton. And so there it is. That is the original Reynolds analogy between momentum and heat transfer. What's on the left side is momentum and the skin friction coefficient. What's on the right side? Nusselt and the heat transfer. Now, Colburn did a modification to this, and everybody uses the modified Reynolds analogy. And he said, because we're trying to fit this to experimental data, it's really the Nusselt over the Reynolds Prandtl and just Prandtl to the 2/3. And you'll find the vast majority of literature put that Prandtl to the 2/3 in. So that you could even simplify it a little bit, Reynolds Prandtl to the 1/3. Take a deep breath. That was too much to swallow. But the book takes a number of pages. Did I encourage you to read the book? If I haven't done that, let me encourage you to read the book. So please read the book. Now let's solve a problem and apply this. Apply these equations, this principle of this analogy. So we have atmospheric air at 15 meters per second approaching and flowing, and 15 degrees C free stream conditions flow over a 0.25 meter square surface. So if the area of the surface is 0.25 meters squared, its length, L by L, take the square root of the area, is 0.5 meters. 0.5 and 0.5, and it flows over. And they give us the U infinity, 15 meters per second. They give us the T infinity of 15 degrees C. Before I move on, there's a key in front of the word air. We understand what air is, but what's atmospheric air? What are they telling me about the pressure of that air? 1 atm, exactly. Now, there's a drag force, they say, that's exerted by the air flowing over it of 0.062 newtons. What is the electrical power required to maintain the surface at 140 degrees C? So think about this. Here it is. I'm trying to just draw it in a simple dimension. There's going to be some electric power supplied to a resistive heater to keep that temperature of the surface 140 degrees C, because it's hot, and it's going to want to transfer Q convection off. How much is the convection? It's going to be HA Ts minus T infinity. So we do an energy balance, and we find that the electric power has to balance what's swept away in the convection. So how do we now calculate this convection? I know the area, I know the two temperatures. What do I not know? The convection coefficient. And then they say, but you're given the drag force? So if this flow is coming at it with U infinity, I'll have to supply a force equal and opposite the drag force that the flow induces going over the flat plate, right? Okay, so the drag force is exerted. What's the relationship between the drag force and the shear stress at the surface? The area. That's exactly right. So they tell us the drag force, you can calculate the shear stress. If you know the shear stress, can you get the average skin friction coefficient over the surface? Wouldn't that be the average shear stress? Maybe I should put average up there. Divided by 1/2 rho infinity squared. I think I can put some numbers to some of this. This boils down to 0.002216. What are the units on C sub F? Dimensionless, right? Just like the Reynolds and Prandtl and Nusselt, they're all dimensionless. Okay, so now we recall our analogy. So we have C sub F average over 2, 0 to L, is equal to the Stanton number, which is the Nusselt average times the Reynolds Prandtl to the 1/3. I'll put it in that form. This is a Reynolds number. Prandtl to the 1/3. So the Nusselt number is equal to C sub F over 2, Reynolds number, Prandtl to the 1/3. I have to start calculating some properties. And when you go, there's a table for air, but it's temperature dependent at 1 atm, but I need to evaluate it at the film temperature. So it's 15 degrees C plus 140 degrees C divided by 2. That conveniently comes to 350 Kelvin, so I don't have to interpolate in the table. So I can get the density that I just needed and used, sorry about that, 0.995 kilograms per meter cubed. I get the viscosity, 20.9 times 10 to the minus 6 meters squared per second. The thermal conductivity, 0.030 watts per meter degree C. And the Prandtl number equal to 0.70. The Reynolds number it's U infinity L divided by nu. This Reynolds number comes in at 3.59 times 10 to the fifth. 3.59 times 10 to the fifth. You tell me, is it laminar or is it turbulent? Answer A or answer B. At the end of the plate, after a L of 0.5 meters, there's the Reynolds number. Is it laminar flow or turbulent flow? My lips are sealed. Flow over a flat plate. Do you need more time or is that good? So I know that I talked about this condition right here, but maybe I failed to emphasize something, but it's emphasized in the prerequisite course, right? What is the Reynolds number at which you would expect to have a transition between laminar and turbulent flow for flow over a flat plate? And a lot of students will say either one of two numbers. They'll say the Reynolds number critical, which is for transition, is either 2300 or 5 times 10 to the fifth. If they say 2300, what are they thinking? Flowing pipes, flowing pipes. If they're saying 5 times 10 to the fifth, they're saying, flow over a flat plate. It has to get up to 500,000. Is 5 times 10 to the fifth 500,000? Yeah. So basically, X critical CRIT is when the Reynolds number equals roughly, I know it's not precise, 500,000, 5 times 10 to the fifth. True? So with that, I'm going to do this. I'm going to ask the same question again, but only 30 seconds. Is this flow laminar or turbulent? All right, we stop. And I can go home and tell my wife will be happy to know that was before my little hint. This is after my hint, right? Well, sorry about that if that messed you up. But there you go. So it is a laminar flow over the plate, the entire plate. So when you plug it into this with the Prandtl number, you calculate that the Nusselt number, the average Nusselt number comes in at 353. It's the H average times L divided by K. So you get the average H is 353 times K, the thermal conductivity 0.030, divided by L 0.5 meter. And you get the average H to 21.2 watts per meter squared degree C. That is a lot of work to get H. But that's basically the challenge of the next few chapters. I know that other textbooks may take a different approach, but this book and the majority of introductory heat transfer textbooks for this type of classes, the goal is to get H. How do you get H? Get the Nusselt number. Once you have the Nusselt number, you unravel it to get H. So now we could come up here and we can calculate what Q needs to be, and it's 660 watts. So you need around electric power of 660 watts. Done. You have just finished chapter 6. So modified Reynolds analogy, it has limited application. Let me just say, this packaged up equation looks great. Straight flow inside of tubes, straight flow over plates. It does not work when you get flow over an object and you get a large WAKE region. All right? It doesn't work. So that's a limited application. Remember those boundary conditions, they had to match up between the momentum and energy equation. Thank you for your attention. We'll see you next time.